Have you ever seen a cereal box? Sometimes the box shows a picture of someone holding that very same cereal box, and on that smaller box, there is an even smaller picture. This effect is often called the Droste effect. It is named after a brand of Dutch cocoa. Their tins famously featured this recursive image. It makes you wonder where it all ends. This playful idea of an image containing itself is a wonderful starting point. It helps us think about a concept called recursion. Recursion is a fascinating idea found in many fields. It is present in mathematics, art, and even nature. Imagine standing between two parallel mirrors. You see an endless line of your own reflections. Each reflection is a smaller version of the previous one. This is another visual example of recursion at play. The core of recursion is self-reference. Something is defined or built by referring to itself. Think of a set of Russian nesting dolls. Each doll opens to reveal a smaller, similar doll inside. This continues until you reach the smallest doll. Let us begin. So, what exactly is this recursion we speak of? In simple terms, recursion is a process where a function or procedure calls itself. It is like a set of instructions that includes a step telling you to perform the entire set of instructions again. But crucially, it usually does so with a slightly simpler or smaller version of the problem. This getting smaller part is key. It ensures that the process eventually reaches a point where it can stop. This stopping point is often called a base case. Imagine you have a task. Let's say you need to clean a stack of dishes. A recursive approach might be, if there are dishes in the stack, take one dish, clean it, and then repeat the process for the remaining stack. The base case here is when the stack is empty. No more dishes mean no more cleaning. This simple analogy shows the two main parts of any recursive process. There is the recursive step, clean one dish, then tackle the smaller stack. And there is the base case, no dishes, stop. Mathematics is full of wonderful examples of recursion. One of the simplest and most classic is the factorial function. The factorial of a non-negative integer n, written as n, is the product of all positive integers less than or equal to n. For example, 5 factorial, written as 5, is 5 times 4 times 3 times 2 times 1, which equals 120. This is a straightforward calculation, but how can we define this recursively? It is surprisingly neat. We can define n recursively like this: if n is 0, then n is 1. This is our base case. It gives us a definite starting point, or rather, an ending point for the recursion. For any positive integer nn is defined as n multiplied by n1. Notice that n1 is just the factorial of the next smaller number. So, to find 5 factorial, we say it is 5 times 4 factorial. To find 4 factorial, we say it is 4 times 3 factorial. This continues until we reach 0 factorial or 1 factorial. 1 factorial is also 1, which can be another base case. Let's trace 4 factorial using this recursive definition. 4 factorial equals 4 times 3 factorial. To find 3 factorial, we use the rule again. 3 factorial equals 3 times 2 factorial. And for 2 factorial equals 2 times 1 factorial. Finally, for 1 factorial equals 1 times 0 factorial, or we can define 1 factorial as 1 as a base case. If we use 0 factorial, our base case says 0 factorial equals 1. Another famous mathematical sequence defined recursively is the Fibonacci sequence. You may have heard of it. It starts with 0 and 1, or sometimes 1 and 1. Each subsequent number is the sum of the two preceding ones. So the sequence goes 0, 1, 1, 2, 3, 5, 8, 13, 21, and so on. This sequence was described by Leonardo of Pisa, known as Fibonacci, in the 13th century. He used it to model the growth of a rabbit population. The recursive definition is very clear. Let fn be the nth Fibonacci number. The base cases are f0 equals 0 and f1 equals 1. The recursive step is fn equals fn1 plus fn2 for n greater than 1. So to find f5, we need f4 and f3. To find f4, we need f3 and f2, and so on. The calculations branch out like a tree. Eventually all branches reach the base cases f0 or f1. Then the values are summed back up. For instance, f2 equals f1 plus f0, which is 1 plus 0, equaling 1. Section 5 echoes in reality recursion beyond numbers. Recursion is not just confined to the abstract world of mathematics, it pops up in many everyday situations and objects. We have already mentioned the Droste effect on packaging. or the seemingly infinite reflections between two mirrors. These are visual examples of self-similarity. The whole contains a smaller version of itself. This is the hallmark of recursion. Think about how you learn a language. You learn words, then phrases, then sentences. Sentences can contain clauses, which are like smaller sentences. Consider a large organization like a company or an army. The overall structure is often recursive. A general commands colonels. Each colonel commands majors. Each major commands captains, and so on, down to individual soldiers. Each level has a similar command structure, just on a smaller scale. Or think about how a book is organized. A book contains chapters. Chapters contain sections. Sections contain paragraphs. Paragraphs contain sentences. Each level is a component of the level above it, often with a similar structure. Even simple actions can be recursive. Imagine you are searching for a lost item in your house. You might decide to search room by room. Section 6. The infinite in a nutshell. Fractals and Recursive Art. One of the most visually stunning manifestations of recursion is in fractals. Fractals are complex geometric shapes that exhibit self-similarity at all scales. If you zoom into a part of a fractal, you will often see a smaller version of the whole shape. This infinite detail is generated by repeating a simple process recursively. Famous examples include the Mandelbrot set, the Sierpinski triangle, and the Koch snowflake. These are not just mathematical curiosities, they are also incredibly beautiful. Let's consider the Koch snowflake. You start with an equilateral triangle, the base case or initiator. Then, for each side of the triangle, you perform a recursive step. You divide the side into 3 equal parts, you remove the middle part, then you add 2 new sides of the same length, forming a new equilateral triangle pointing outwards. Now you have a more complex shape. You then apply this same rule to every straight line segment of the new shape. Repeat this process infinitely, and you get the Koch snowflake. The Sierpinski triangle is another fascinating example. Section 7. The computer's clever trick recursion in code. In the world of computer science, recursion is a very powerful tool. Programmers often use recursion to write elegant and concise solutions to complex problems. Many algorithms are naturally expressed in a recursive way. This is especially true for problems that can be broken down into smaller, self-similar subproblems. For example, sorting a list of numbers can be done recursively. One famous algorithm, quicksort, picks an element, the pivot, and partitions the list into elements smaller and larger than the pivot. Then, it recursively sorts the 2 partitions. Another common use of recursion in computing is for traversing tree-like data structures. Think of the file system on your computer. It has folders, and folders can contain files in other folders or subfolders. This is a hierarchical or tree-like structure. To find a specific file or to list all files, a program can use recursion. A function might check the current folder. If it finds the file, great. Section 8. The bottomless pit, when recursion goes wrong. While recursion is a powerful and elegant tool, it comes with a caution. Like a magical spell, it must be handled with care. The most common pitfall is creating an infinite recursion. This happens when the recursive calls do not properly lead to a base case, or perhaps the base case is missing entirely. Imagine our Russian nesting dolls again. If there was no smallest doll, you would keep opening them forever. This is precisely what happens in an infinite recursion. In a computer program, each time a function calls itself, the computer needs to remember where it was. It needs to store some information, like the current values of variables. This information is typically stored on something called the call stack. If a function keeps calling itself without ever stopping, the call stack keeps growing. Eventually, the computer runs out of memory allocated for this stack. This results in a stack overflow error. The program crashes. It is like trying to stack too many plates. Eventually, the tower topples. Section 9. Recursion's Grand Design, a Universe of Self-Similarity. As we have journeyed through the world of recursion, we have seen its remarkable reach. From the simple act of looking into mirrors to the complex structures of fractals. From the definition of mathematical functions to the algorithms that power our computers. Recursion is a fundamental concept. It is a pattern of thinking. It is a way of building and understanding complexity from simple, repeating rules. It is like an echo that reverberates through many different domains of knowledge. The beauty of recursion lies in its simplicity and its power. A few lines of a recursive definition can describe an infinitely complex object like a fractal. A simple recursive algorithm can solve a daunting computational task. Nature itself seems to employ recursive strategies for growth and form. The branching of trees, the unfurling of a fern, the spiral patterns in shells and galaxies. These all hint at underlying recursive processes. It suggests a universe that enjoys repeating its patterns at different scales. Recursion teaches us to look for self-similarity. It encourages us to break down large problems into smaller, more manageable pieces that resemble the whole. This way of thinking is not just useful for mathematicians or computer scientists. It can be applied to learning, problem-solving, and even artistic creation. Understanding recursion opens up a new perspective on the world around us. It allows us to see the intricate connections between seemingly disparate phenomena.